Hello students, let us start our session of chapter 13, Kinetic Theory. Kinetic theory basically defines the behavior of gases. These gases are made up of very tiny small atomic particles, and these particles are moving rapidly randomly in different direction with different velocity. So here kinetic theory explains this behavior of gases. Between these molecules, forces existed. This force is depending on the distance between these molecules. As we know that distance between molecules are very much less in solids and liquids as well. This distance between molecules is very much higher in comparison to solid and liquid, that is in gas. So here we can say that these interatomic forces, which is known as a short range forces, which is present in solids and liquids, and this force is very less for gases, which is negligible. As the distance between molecules is increases, then effect of force gradually decreases. Here this kinetic theory was developed in 19th century by Maxwell, Boltzmann and other scientists. Here, this kinetic theory gives the molecule interpretation based on pressure and temperature, as temperature and pressure are the variable parameters which are affecting on gas molecules, and as a result, volume variation can be observed in the gas. So here, it consists with many gas laws and Avogadro hypothesis. So here, this kinetic theory explains specific heat capacity of gases based on viscosity, conduction, diffusion with molecule parameters, and as a result, it estimates molecule size and mass. Now let us understand molecular nature of matter. Here matter, which is designed by using atoms. So this statement is given by Richard Feynman. Another important hypothesis is available for the atoms. Here it defines that all things are made up of atoms. These little particles, they move around in a particular motion which attracting each other when they are at a shorter distance, but it repels upon each other when the distance gets reduces. So here, while these atoms are apart from each other with some distance, then they provide the attraction force between them and they will give the velocity of this atomic structure. While they come nearby to each other, collision takes place, and based on that, after collision, they will move in a different direction as the direction and velocity gets changed, and this repulsive forces existed between them. Now let us understand the atomic theory which is proposed by John Dalton. Here he explained the laws of multiple proportion of the elements when they combine together and generate the compounds. So here he provides two laws. First law that whatever the compound is available, which is generated by the combination of constituents. So here the given compound has a fixed proportion by the mass of its constituents. In second law is given by him that when two elements form more than one compound, then for a fixed mass of one element and the mass of other elements are available in the ratio of integers. Here atoms of one element which is identical. Here small number of atoms of each element will combine to form a molecule of compound. Let us go through the Luzak's law. He defined that when gases combine chemically to generate a response or another gas, then their volumes are in the ratio of small integers. Another hypothesis is given by the Avogadro, and he defined that when we are having number of gases in which they will occupy the equal volumes at equal temperature and equal pressure, then number of molecules are consisted which is having a same number. So here, when this Avogadro hypothesis law is combined with the Dalton theory, then it will give you the Luzas law. So here, the elements are often in the form of molecules. Dalton's atomic theory can be referred as a molecule theory of matter. These molecules are made up of one or more atoms. These molecules we can see using electron microscope and scanning tunneling microscope. By observing these molecules through these devices, we can see that size of the atom is available in angstrom in 10 raised to minus 10 meter. Now, in solids, as we have seen that interatomic force is existed because of the shorter distances available between molecules. Here, this distances also can be observed by using microscope and scanning tunneling microscope, in which the distance or the atoms are spaced in solid and liquid by the 2 angstrom, and this space is available in gases in range of tens of angstrom. So here, this interatomic distance is less, due to that effect of force is again very less. So here, while these molecules in gas are moving in free space in random direction with the random velocity, so here we are supposed to define that average distance is covered by molecule while it is traveling without collision, that this average distance is known as mean free path. And this mean free path is available in gases in the order of thousands angstrom. These atoms are free in gases and they can travel longer distance without any collision. So here this gas or these molecules, then we need to bound with enclosed container, otherwise these gas molecules will move outside and gas will disappear away. Now, in dynamic equilibrium, these molecules will collide and its direction and speed will change. Ultimately, its velocity gets changed. But here their average properties remain constant, just like volume or the macro level properties which remain constant. Here they consist or they design by using a nucleus and electrons. And in atomic structure, at the center, the nucleus is available. Around this nucleus, in the orbital path, electron is traveling. At the center, in the nucleus, which is designed by using protons and neutrons. Electron is having a negative charge, proton is having a positive charge, and neutrons are electrically neutral. So in one atom, the number of protons and number of electrons are same. It means that atom electrically always remains balanced. These protons and neutrons are designed by using quarks. Right, is it clear? Now let us understand the behavior of these gases. In this gas, molecules are far away from each other and their mutual interaction or collisions are negligible until and unless they will collide, then only its interactions can be possible. Again, this collision is not often, it's not that much frequent. So here, these properties of gas can be easy to understand as they are far from each other and their interactions are less. These gases at low pressure and high temperature, they will give a liquefied or solidified result. So here we know that the relation between pressure, temperature and volume, that is PV equals to KT, where P is the pressure, V is the volume, T is the temperature, absolute temperature in Kelvin, and K, that is the constant value, is available. This K is constant for the given volume of gas. So here that K is depending on the amount of volume. If volume gets changed, number of molecules gets changed. So this capital K, that is proportional to the number of molecules N. And while we remove this proportionality, that is substituted by constant small k, which is denoted as Boltzmann constant. So here, if we are taking two gases having the value P1, V1 equal to KT1, or substitute that value of K with N small k. So we can say that P1 V1 equal to N1 KT1 and P2 V2 equal to N1 KT2. So by taking the ratio, we can say that P1 V1 by N1 T1 equal to small k, Boltzmann constant. Same for the another gas, P2 V2 divided by N2 T2, that would be equal to small k, which is Boltzmann constant. So now Boltzmann constant having two equations for different two gases, we can be equated and will give the result P1 V1 by N1 T1 equal to P2 V2 by N2 T2, that would be equal to constant, that Boltzmann constant. So here this ratio, that pressure, volume and number of molecules with temperature, that ratio will give you always a constant, Boltzmann constant. Now let us define that the pressure, volume and temperature, if we are keeping constant based on the Avogadro hypothesis, if we are making P1, P2 equal to P constant, V1, V2 that would be equal to V constant, and T1 and T2 that would be equal to T constant. So we are getting the result 1 upon N1 equal to 1 upon N2 equal to Kb, ultimately can be defined as N2 equal to N1 equal to Kb. It means number of molecules are present, that is again constant. So here this is how we can prove the Avogadro's hypothesis. And this number of molecules N, which is denoted as Na. This Avogadro number is 6.02 into 10 raised to 23 for 22.4 liters of gas. And while we are taking this the mass of 22.4 liters of gas, that would be equal to, in the molecular weight in grams at the standard temperature 273 Kelvin and 1 atomic pressure. So this value of the Avogadro number we able to get 6.02 into 10 raised to 23. Now we are having an ideal gas equation, PV equals to mu RT. R, which we know constant, Na Avogadro number into Kb Boltzmann constant, and mu is the number of moles present in that gas. T will give you the absolute temperature in Kelvin, and R, by substituting the value of Avogadro number and Boltzmann constant, we are having a value R equal to 8.314 joule per mole into Kelvin. That mu, we know the number of moles that can be, that we are having that equation m by m0. that would be equal to N by Na. That capital M, that is a mass of gas having N molecules. M0, that is a molar mass. Na is the Avogadro number. And N is the number of molecules available in that particular gas. So here, let us substitute the value of mu from the ideal in the ideal gas equation. So PV equal to mu RT, right? That R can be substituted by Na into Kb. So it would be like mu Na Kb into T. Now mu into Na can be substituted by N from the equation 13.4. So we will get PV equal to N into Kb into T. That is what P dot V equal to N into Kb into T. Now if we want pressure only, then at both the side it would be divided by the volume. So here, while we know number of molecules that give you amount of the volumes. So here this N, capital N by volume V, that would be equal to small n, that is the number density. So P equal to Kb into small n into T, that will give you the number density. Kb will give you the Boltzmann constant, that is 1.38 into 10 raised to minus 23 joule per Kelvin. Now, let us go through the graph which is available between PV by T and pressure. So here, as we know, the ideal gas will define as a PV by T value is constant by variation in the pressure. So if the pressure variation we are providing, the value of the ideal gas remains constant. Now, if for the natural gas where we are discussing, so while we are focusing for the different temperature, then we can see that as the temperature is increases from T3 to T2 to T1, then this graph, this approach will moving towards the ideal gas. Now, let us discuss the pressure volume graph, PV graph. Here we are maintaining mu constant. Here in the PV graph we are taking temperature also constant. So here by keeping the temperature constant, change the value of pressure and verify the value of volume. So here solid line that will give you the gas result and dotted line that will available for the Boyle's law. That we know in the Boyle's law, we are taking temperature constant and verifying the result between pressure and volume, and we can define that pressure is inversely proportional to volume. So here as the pressure is increases, volume gets reduces. This Boyle's law is identified for the dotted line at a different temperature. Now here also we can observe that T3 solid line and T3 dotted line, there is a basic very larger differences available in its graphical representation. When temperature is increased from T3 to T2, that difference gets reduces, but it is again available with the larger value. And while again we are increasing the temperature from T2 to T1, then we can see that the behavior of gas which is approaching towards the ideal Boyle's law condition as T1 solid line and dotted line you can observe. Now, let us understand the TV graph. Here that gives you the Charles law condition. In Charles law, as we know that from the ideal gas equation, we are keeping pressure constant and verifying the effect of temperature over the volume. So here we are verifying that how the temperature gets changing and effect of that volume variation we are defining. This variation we are observing by keeping the pressure constant. So let us keep pressure P3 constant and compare the solid line of P3 with the dotted line. Then again increase the pressure from P3 to P2 and we can observe that how these particular lines will available towards that ideal value. And while that again pressure will increase from P2 to P1, then we can say that we can get more ideal equation, or we can say that more gas is moving up, approaching towards that Charles law condition. Now let us take more than one gases and interact, provide the interaction between them. So here if we are saying that these particular gases are not reacting chemically to each other, it means non-reactive ideal gases are there which we have mixed. So here for gas 1 which is having a moles mu1, for gas 2 having a moles mu2, and in that particular vessel the total volume is covered by the combination of gases V and it is available at the temperature T and pressure P. So here PV equal to mu RT, but this mu is not for the single gas. For the different gas, number of moles are different and we can combine separately with mu1 plus mu2 plus mu3. Now take the volume at other side, at right side in the denominator. So P equal to mu1 RT by V plus mu2 RT by V plus mu3 RT by V. So that mu1 RT by V will give you the pressure 1, mu2 RT by V will give you the pressure 2, and mu3 RT by V will give you the pressure 3. So total pressure that would be equal to P1 plus P2 plus P3. Here we can say that total pressure, that is a combination of partial pressure of gas, which is known as Dalton's law of partial pressure. Is it clear, everybody? Here we are going to end the session. Hope you understood. Thank you.